Hello, this is Reese Harris, Mr. Harris. I'm walking through more examples. This is AP Stats Unit 9, video number 3. Let's work through this example just to practice setting up our null and alternative hypotheses using mu, and then shading in our normal distribution. We're going to talk about adding actual values to our normal distribution, and then practice shading with certain alpha levels, whether it's alpha divided by 2 because it's equal to or not equal to, or if it's just a straight up and down alpha because it's only a one-tailed test. Okay, so looking at this example 2, a chemist invents an additive to increase the life of an automobile battery. If the mean lifetime of the automobile battery is 36 months, then her hypotheses are. Again, using our context clues, if the mean is, so if it's is, as based off of video 2, is, it is, or it isn't. So I'm thinking equal to or not equal to. You can already see in example 3, the average wishes to lower. So when they're talking about more than or less than, that's an indication it's a one-tailed test. But if it is or isn't, you know it's a two-tailed test. So for me, I always find it easier to set up the alternative hypothesis. Again, the hopes and dreams of this chemist is in the alternative hypothesis. This is what the chemist needs to find supporting data for. So they are talking about the mean, so we're sticking with a mu. The alternative relative to 36 months. If the mean lifetime of automobile batteries is to increase. I'm glad I read this again with my active pencil because I notice increase. So they're telling us the mean, the status quo is 36 months, but the hopes and dreams and wishes of this chemist is to increase. So we want this mu to be greater than 36 months. Since I'm at the alternative, I'm already gonna go ahead, let me lay my stake. This would be my test statistic. And we would be shading to the right in the direction of the inequality of the alternative. So whatever our test statistic is, relative to our alpha. So this is our test statistic, yet our alpha is somewhere out here. Then as long as we're to the right of the alpha, then we have evidence to support the alternative hypothesis. The alpha would be our inherent error. The shaded region to the right of whatever our test statistic would be, that's where we get our p-value from. So let's say we were told we were going to be 95% confident, or our alpha is 5%. 95% is here. Everywhere placed to the right of alpha is 5%. In this case, we're in the region where we can reject the null and accept the alternative. And in this case, it looks like, let's say our p-value would be somewhere around maybe 3%. So as I share the screen again, a p-value of 3% would mean it's highly significant. If that were the case, based off of whatever test statistic we get from our mean from our sample and our sample size, our sigma divided by square root of n for our standard error. Our test statistic in this case would come from the equation, because we're talking about means, x bar minus our status quo mean divided by sigma divided by square root of n. This would be our test statistic for our sample data. So that's our alternative. The null is literally just mu. If that's greater than, then the null is mu is less than or equal to 36 months. And that's it. So we're going to work through the mathematics of this. Isn't that difficult? You did use this equation in unit 7 and 8. And that we actually work with this equation, I think from units 3. So the math isn't that bad. It's just fighting our way through the proverbial dark forest, if you will. And as stated, the test is a right-tailed test since the inequality sign for the alternative hypothesis points to the right. And we know it's a right-tailed test because the chemist invents an additive to increase. We have to focus on these context clues and be very careful. Read it 2 or 3 times and use your active pencil just to keep track of what you need. Again, pause this. If I were you, I would try to do example 3 on my own, then check. Then I would do example 4 on my own, and then check, just to make sure this doesn't trip you up. I'm going to go ahead and work through example 3. A contractor wishes to lower, context clue, heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, so I'm going to say we're told the status quo, mu is $78. Her hypothesis about heating costs, if the average of the monthly heating bills is $78, her hypothesis about the heating costs with the use of insulation are, the null, mu is, we're talking about lowering. I want to start with my alternative because it makes sense to me. Do what works for you. The contractor's wishes, hopes, and dreams are to lower heating bills. So if the average heating bill is $78, we want to lower it. So we want mu to be less than 78 using their insulation. If this is less than 78, then the null is that it's greater than or equal to 78. So you see how, again, all nulls include the equal sign. So it includes what we're given, that the average is 78 or anything higher. So the only way this will be supported is if the evidence says that the average heating bills are truly less than, significantly less than, meaning our error is low enough where we can have some faith that this insulation does work. Let's say this were, instead, let's say our alpha was 10%. That means there's 10% here, 90% here, and we're going to shade over here. And let's say in this case, our test statistic after we calculate it lands us here. That means we fail to reject the null hypothesis because we're not in this region. Our p-value would be more than 10%. Our error is 10% because we're willing to just be 90% confident in this case. But if our test statistic lands us here, that means we have an error of maybe, I don't know, 20%, which is not good at all. But we don't have to do all of that yet because we don't have all the information. We're just setting up the null hypothesis, the alternative, and generally shading what that graph would look like. Notice this is also a one-tailed test. Notice I did not divide alpha by 2. The importance of that single word, lowering a heating bill. Okay. Left tail test. I'm going to begin example 4 now. Suppose we wanted to determine whether a coin was fair and balanced. A null hypothesis might be that half the flips will result in heads and half in tails. The alternative might be that the number of heads and tails would be very different. Symbolically, these hypotheses would be expressed as. Notice there's no indication in the context clues or the wording, more than, less than, greater than. So I'm thinking it's just, it is or it isn't fair. So whatever the half the flips would result, fair and balanced, the number of heads and tails would be very different. Instead of mu, I'm going to use P for proportion. So the alternative is that it's not fair. Fair and balanced, 50%. So I would say that the proportion is not 50%. And for the null, the proportion is equal to 50%. And that's how you can tell if they're talking about proportions versus means. There's no indication about average, but they do mention half the flips would result in. Two-tailed tests. Here, this would be our alpha divided by 2. So if this were 95% here, then over here, it would be at 97.5 and 0. Let me just stick with percents instead of going to decimals. 2.5% would be out here. 2.5% would be out here. 97.5% of all the data would go from here up to here, but we don't want to include that. The next step, we will look at our z-score and our inverse norm to figure out how to get the exact z-table values. Generally, just like the confidence interval unit, if you're doing 90%, 95, 99%, there's certain numbers, you use it so much, you'll just remember it. For those that wish, here's steps, but I'm gonna work through enough of these. I don't even know if you'll need these steps. But if you wanted to take a screenshot or read this or pause it, general steps. Okay. So these are just examples. Let's start with the left tail test. Remember, we start from the alternative hypothesis. Mu is less than, so we shade to the left. These are different alphas. Alphas would be our error. So if our alpha is 10%, that means we have 10% error here. 90% is over here. Our critical value, negative 1.28, that's essentially the line of demarcation. So if this is 10%, 90%, the z-score value, negative 1.28, that's where our test statistic would have to either be less than in order to reach significance or greater than to not reach significance. I'm gonna look this negative 1.28 in my z table. Negative 1.28. And they're like magic, negative 1.28 is 10%. So that's where 10% is to the left of that line of demarcation, that stake in the ground, and 90% would be to the right. Jumping here, right tail test, it's the same thing. If you notice, instead of it being negative 1.28 here, it's positive 1.28 because we're on the right side. And then down here, two-tail test, if you notice 10%, let's look at this number. We know 10%, it won't necessarily be what we need. That is actually plus or minus 1.645. If you recall this from the confidence interval unit, because here we have to do alpha divided by 2 because it's split in 2. So I'm gonna try to find, I bet you if I look up negative 1.645 here, instead of there being 10% of the proportion of the data, there's only gonna be 5%. Negative 1.645. And probably just 1.64. You see? Yep, just 5% of the data. So that's what happens when it splits. Remember, the graph is oblong, so it's not gonna intuitively gonna be way out here, way out here. The further we go out, the less total proportion there is as we go out. Let's find positive 1.645, and we'll see that that should be, I believe 97. No, 95%. Positive 1.645. 95% of the data, so please be very careful with that. Okay, and I'm gonna walk you through 3 examples. If you wanna look at this, fine, but the next thing and the last thing from this video 3, I'm going to walk you through examples where you're actually graphing and plotting and calculating those data points. Okay, so here we go. And I suggest maybe work through some of these and then try some on your own. Lay your stakes, shade your critical region, label the graph showing the critical region, the non-critical region, and the z-value. So let's start off here. We know it's a two-tailed test because it's equal to, not equal to. I'm gonna draw my flags. You can stakes, flags. This is the line of demarcation where if our test statistic goes beyond, it's significant. If it doesn't go beyond, it's not significant at the alpha equals 1%, at the 1% level. That's pretty strict, by the way. If you wanna be alpha 1%, that's strict. If it doesn't work, maybe you can get away with 5%. Dollar store level stuff, the alpha is not 1%. Dollar store is low quality, cheap. They save money. They don't have as many workers. They don't hold nearly as high a quality control check procedures for their products. If you've bought in those wooden puzzles from the dollar store, you can even get splinters. They're not even sanded properly. They're okay with 20% error. They'll live. If you're talking about medication that can kill people, you need to be at this 1% or less alpha. It depends on the context of whatever you're dealing with. Two-tailed, I'm going to automatically shade out here. Because it's two-tailed, it has to be alpha divided by 2 because we're dividing it by 2. So that's 0.005, 0.005. In between here, this is 99% or 0.99. So the non-critical region, non-crit region, and then there's 2 critical regions, here and here. So whatever our test statistic is, if it lands here, it's significant. If it lands here, it's significant. If it lands here, we can make an argument that's significantly less than, or we can make an argument that's significantly greater than if it's over here. The whole point here is we want to see that it's actually different. I'm going to look up 0.005 in my z-score table, get my z-score values, and then I'm going to use my calculator to do the same thing. So 0.005%, remember for percents, proportions, we have to dive directly into the table. 0.005. We're close, yep. And hopefully this number should look familiar. Negative 2.57, maybe 2.575, and that's the left tail. The normal distribution is proportionate, so it's going to be plus and minus 2.57. Let's flip this over and look for positive 2.575, 2.575-ish. And you notice if we add 0.005 here, we will be at 100%. So that's the opposite of that. So these would be the z-score values, negative 2.576, negative 2.575, whatever. Computers do all that work for you. So if it's two-tailed, make sure you have the negative and the positive version. I'm going to now use my calculator and use the inverse norm feature. Okay. So inverse norm, because our alpha has everything to do with the proportion. We are talking about the normal distribution. We're not at t distributions yet. Our area for the left end, 0.005. Please remember to divide your alphas by 2. Let's do that just to make sure. 0.01 divided by 2. That's where we get 0.005 from. Inverse norm. Mean is still 0.005. Mean is still 0. Standard deviation is still 1. negative 2.57576, and that gives you the left end. You see the importance of drawing your picture? It reminds you that there's a negative and a positive because it's a two-tail. Please draw your pictures. Uh, and that's how we do that. It's important to identify if it's a two-tail test so you can plug in the proper alpha and get the correct critical values. Whatever our test statistic is, if our test statistic is greater than 2.576, we have evidence to reject the null and accept the alternative. If our test statistic is less than negative 2.576, we have evidence to reject the null and accept the alternative. If our test statistic is any number between these, we lack evidence at the 1% level. We may have evidence at the 5% level. We would have to recalculate. Switching screen time. That's why here we're talking about if you're not significant here, you might still be significant here. In this case, maybe we need to go out 9 more decimal places. That's when you're sort of teetering on the edge and, well, if I do this, if I do that, maybe I can push the limits. Depends on what's going on here. And just because you're not significant does not mean your product doesn't do anything. That's the issue. There is an issue in the scientific community with significance. Again, these are these researchers' hopes and dreams, and it simply falls down to a number. Just because it's not significant at the 5% level doesn't mean it doesn't do anything. It's just there's not enough evidence to support certain industries backing up what you say. But if there's a 20% chance that it doesn't do anything, some people will still work with that. You just have to weigh the cost benefit analysis. How much are you paying for this treatment? What are the adverse side effects? Things like that. And also, this kind of strict research does require money. A lot of people don't want to invest that money. They'd rather just sell something over the counter. As long as the side effects are not harmful, certain things you can or cannot get away with it. Thank God we have the Food and Drug Administration. Some people don't like it because it does tie things up, but there is some level of some layering of some critical analysis. So whatever doctors are prescribing to us, we're taking over the counter. If it doesn't do anything, at worst, we're out some money, but it doesn't cause huge adverse side effects. We would hope that. So I'm going to work through the rest of these. Try to do some of these on your own. Starting with our alternative hypothesis, I'm going to put a generic stake here, shade to the left. You don't have to do flags. I just like doing flags because why not? Our alpha is 10%. 10%, so we would be at the 10% level of significance, which isn't that great, but I mean, if we're just looking for product for dollar stores, that's perfectly fine. Depends on the context. Again, 90%. This is our non-critical region. This is our critical region. Crit region. Let's find a z-score using our calculator. And again, if you do enough of these, you'll sort of memorize it, except confidence intervals are always two-tailed. So based off the last unit, these will be different because they are one-tailed. That's why it's good to use your inverse norm. The area to the left is 0.1, negative 1.28. So we would look for a test statistic that's less than this in order to have enough evidence to support accepting the alternative hypothesis. And that's it. Here, for this next one, we have to divide this by 2. Yeah. It's a two-tailed test. That's why we have to divide it by 2. Still 95% here. 2.5% here. 2.5% here as well. We're not going to be calculating from this up. From this up would be 97.5%, but it's just 2.5% of the data on the extreme right, above, 2.5% of the data on extreme left below, everything in between. I'm going to find my critical values for my z-scores. 0.025, remember we always plug in the proportions. Negative 1.96, which we are used to from the confidence interval unit. Positive 1.96. So that one we're used to. I will take the time to remind you of this handout. Enough of these you use enough, but this is all based off of alpha being divided by 2. If alpha is not divided by 2, we have to, I'm like, use these, but make sure you always double check with your inverse norm, because that's why it's so important to identify, is it a two-tailed or a one-tailed test? That makes a huge difference. So again, there's 2 more. Try to do these on your own and then check. Right-tailed. Let me do my little flag. So 90% is here. This is my non-crit region here. And remember, your calculator inverse norm naturally shades from the left up. So I would type in 0.9% because it's 90% here, alpha's 10%. And you know it's a positive 1.28. And good job. Up here, we recall, in this case, we have the negative 1.28, so we know it's working out. But we're on the right side, so our z-score would have to be greater than positive 1.28 to be statistically significant. Lastly here, left-tailed. Left-tailed, 99%, alpha's 1%, non-critical region, critical region. Second distribution, inverse norm, 0.01%. Negative 2.33. Okay. And that's our z-score critical value. That's it for this video. Look forward to video number 4, where I will be working through a complete problem. This is an example of the problem I'm working through. Step by step by step by step by step. Okay, take care.